Hi, this is Rorik Peterson, and this is a short video tutorial on floating point representation for es201. And what we're talking about here is the idea of an exponent and a mantissa, and I want to show how you can come up with what those values should be. So here's the example I'm going to do. We're going to go ahead and we want to represent the number 6.614. And this is a floating point number, a decimal value. And we're going to go ahead and attempt to represent it with a 6 bits over here, where I'm going to use these 2 bits for the exponent and 4 bits for the mantissa. And let's determine which bits need to be turned on. So remember that what I want is I got 6.614, and I want to have that as a number that is 2 to the e power times m, where e is the exponent and m is the mantissa. And e is always going to be an integer value. It can be a signed integer. And the mantissa, if you remember, is going to be a number that is going to be fractional. And then there's the hidden bit, the 2 to the 0 bit, that's always set right over here. And so we know that this is going to be 2 to the e, and the mantissa is going to be 1 point something, because 2 to the 0 is going to be the 1, and then we're going to be adding the fractional components on the right hand side. So with that, we know that the mantissa is going to be some number. It's going to be greater than 1, but it's going to be less than 2, because it could be 1.00000 or 1.99999, but it's going to be between 1 and 2. So that way we can actually determine what the exponent is first. So we'll go ahead and look at the 2 options. And so if the mantissa was equal to 1, then what we could do is we can go ahead and solve for e. We would know that 6.614 is equal to 2 to the e power. And now I'm going to go ahead and solve for e with the lower range of the mantissa. So we take the log of this. We would determine that the value there of e would be about 2.72. And if the mantissa was its largest value, which would be close to 2, that could be 1.999, but we'll just use 2 for that, I would then see that it would be 3.307 would be equal to 2 to the e, because now I'm dividing by 2 to the 2 power. And so, or sorry, dividing by 2, which is what the mantissa is. And then I would find out the exponent would be 1.72. So those are the range that the exponent could be. The exponent has to be an integer value. So therefore, we know that the exponent is going to be equal to 2. So now with this, we can now go ahead and solve for what the mantissa is, because now we know that 6.614, which is the number we want, is going to be 2 to the 2 times m. So now let's go ahead and divide by this 2 to the 2, or divide by 4. So 6.614, we'll go ahead and divide that by 4, and we find out that's equal to 1.6535, right? And that's 1.6535, okay, so that's equal to what the mantissa is. And here's the 1, that's by the hidden bit. So what we need to do now, if I look at our four bits that we have, is that we want to represent 0.6535 in 4 bits. So if I look at my 4 bits that are right up over here, the first one is going to be 2 to the minus 1, and then 2 to the minus 2, 2 to the minus 3, 2 to the minus 4, and those values would be 0.5, 0.25, 0.125, and then the smallest one would be 0.0625. And so let's figure out which one of those components we want. Well, we know we want to set the first bit because it's going to be at least 0.5, so I'll go ahead and set that bit there. If I set the second bit, I would be adding a 0.5 to a 0.25, to the 1, it'd be 0.75, so I'm not going to want to set that one. If I added 0.125, then I would have 0.625, which is pretty close, so I'm going to go ahead and set that bit there. And then the question is, do I want to go ahead and add this last 0.0625? Do I want to set the last bit? Well, let's look at this. So if the mantissa, if I didn't set the last bit, I'd have 1010. And so then what the value would be, if I add up just those 2 values, I'd 0.625. That's the 0.5 and the 0.125. And if I did that, the error between this 0.625 and the 0.6535 is 0.0285. Now if I had set the last bit, I'd have 1011. If I add up those, that would be 0.6875. And the error for that one right there would actually be 0.034. The error being the difference between what the mantissa is that I get with the binary representation versus the number I'm looking for. So this top one has a lower error, so I'm going to have 1010, so there's going to be what my mantissa is. And then remember, the exponent I'm storing is a 2, and so I'm going to go ahead and set that bit and not that bit. This is the 2 to the 1 power, that's 2 to the 0 power, and so that's going to give me that. So now my floating point representation at 6 bits is 10, 10, 10, and I'm going to be having a value that is not quite perfect, but it's going to be pretty close. Okay, hopefully that helps. It's just sort of a demonstration of how to do it.